calculation of moment of inertia, radius of gyration, and polar moment of inertia. We'll be using this track frame example. Generally, they are made using two C channels. You can see one here, another one there. So two C channel, long C channels. That's how they are made. So in this example, I have so this is the 2C channel. Also, we added a section on top just to make the calculation a little bit more interesting. So in a lot of time, there is a bed for the truck to carry stuff. So there will be something on top as well. So the first step in calculating the moment of inertia or area moment of inertia is to find the centroid of the combined piece. And then the second step is to apply the transfer formula. So it is the total moment of inertia is the moment of inertia with respect to its own axis plus the area times the distance is square. So that is from this distance is from the centroid. So let's first calculate the centroid for these three piece. So we're taking a cross section of this track frame, and there is a kind of like a bed going like across the length of this frame. So for the C channel, C 15 by 14, so we can see this is 15 inches. So then to calculate, remember we develop a table to calculate the area, calculate the centroid. So from the table, I extracted the area for the C channel is 11.8, and the Y, because this Y is 15, the half of that. So here is our reference axis. So when you calculate the centroid, you need a reference axis, and that is the bottom. In this case, we are using this is our reference axis, the bottom of this frame. So from the bottom of this frame to its own centroid of this C channel is half 15 by 2. So this distance is 15 by 2. So that's how we got this 7.5. Now then you multiply this area times the, so the formula for the y bar is equal to summation of a y divided by the summation of a. Simple as that. So here, then we're going basically the same for the other C channel, but for the flat sheet on top, that is 0.2 inch thick. So you got from the reference axis is the 15 inch plus half of this. So this is where in the middle is the center of gravity for this flat sheet on top. So it's actually 15 plus 0.2 by 2. So that gives you 15.1. And then you can get the total area moment, and then the simply this 10.43 is AY divided by the area. So this is what we got is simply 400 divided by 38. So this is 400 divided by 38.4. That we found 10.43 inches from the bottom. So the centroid of this overall frame, overall structure is right here, which is 10.43 from the bottom. Now, to calculate the overall area moment of inertia for this entire structure, we need to find that D for each of these three pitches. So this is the centroid for the C channel for its own centroid, and the overall centroid is right here. So we have to find out this D. This is the dy for this one of the channels. So that would be 10.43 minus 7.5. So this is 7.5, half of 15. So then we find that 2.93, 2.93, and then we have to find out the centroid. This is this D. So this, the middle of that to this centroid. So this is the dy for the flat sheet. So that one we can simply do. So we can do 15.1 minus 10.43. So that will give us this 4.67. So you got all the distances from the centroid, the overall centroid. Now we can add. Now I suggest you make a table like the way it is shown here. It's very simple, easy. It will remove all of your thinking. So then you do AD square. And that's what I found for AD square. This IXO, I found it from the back of the book. In the table, you can find it for the C15 by 40. This one is calculated by simply applying the formula 1 by 12 BH cube. So then you have all of these, and then you can add this AD square plus IXO. The total with respect to its own center of centroid, which is 10.4 inch from the bottom, is 1221. That's what I found. Similarly, you can calculate for the y. This is the IYY. Now, the IX, that is you're calculating basically for the cross section, but for this, so it is with respect to the center of gravity, centroid, and for IXX. Now you can also, so the IYY, you can calculate that one too. We calculated that one is 12,982. The only thing you have to be worried about here is simply you can get this IYO from the back of the table, and this one is again 1 by 12 BHQ, but in this case that the base kind of changes from, so this was now height, and then the base becomes that 64 inches length. So this actually then becomes this quite a big number because you are doing 64 cube. Now the distance from the centroid, so what you're looking at here for D is this piece. So this is the centroid, and this is the center. This is where the center of the C channel. So the way you calculate basically the total 17, and then this distance is given in the table in the back of the book, X bar, which I think 0.7 some numbers. So if you subtract that, so this will give you that 16 point, what do you got, 22. So this is 16.22. That's what I got. So you just have to subtract. So 17, this came from the 34 by 2, half of that. That is 17, minus the X bar. So that will give you the distance from the centroid right here to the C channel. And both of them same distance away. Plus minus doesn't matter because we're going to be squaring them. So that's how we got that IYY. Now, radius of gyration. So now explain a little bit. So this IXSY, later on in the beam design section, you will see that the IXX in this case for the cross-sectional area moment of inertia with respect to this axis, XX is related to load coming from the top. So load coming from the top is associated with that IXX. So the stronger, the higher the number for IXX, the higher load it can carry coming from the top. Now the YY that you calculated, IYY, which is related to load coming from the side impact. So the higher the number for IYY, the stronger it is to resist a side impact coming this way. So now the couple of more things is the radius of gyration generally related to the buckling of the frame. It is 11 to when you're talking about columns. So radius of gyration is x. Simply you do Ix divided by area is square root of the whole thing. The Ix area we found 1221, and area again doesn't change, 38.4. If you square root that, I found that piece 5.64 inches. This is very similar to, sorry, that is x. Very similar to the the moment of inertia, but it is 11 when you're doing column. Later on in chapter, we'll be discussing columns load calculation. And Ry, similarly, radius of gyration with respect to y is simply y divided by a, and then y, we found that 12,982 divided by the area is the same, is square root of that, and that's why I found 18.39. That is Ry. Now the polar moment of inertia, simply you add these two Ix and Iy. So this is the polar moment of inertia expressed by J, Ix plus Iy. Generally it is related to the overall rigidity, overall ability to carry load. It mostly apply for shaft. Later on, we'll discuss how to design shaft. That's why you'll be using this polar moment of inertia. So simply to summarize, make a table and let's follow this step. Very simple. Sometimes the mistake would be to figuring out the distance appropriately, but not really that of a big deal. If you just be patient, use the table, it should be good.